This is where we left off in 2.1. So let's continue, do some problems. So this was the general concept of limits. Okay, so we want to talk about then the limit definition. Well, not the definition yet, but what that really means. So let's take a look at this next example. So write this down. Let's show that the limit does not exist of absolute value of x over x. So this is kind of your example that you want to keep in mind as you go through problems of one that's not going to work, basically. So let's first recall that absolute value of x can be defined in a few ways, but for us, we want to define it in the piecewise continuous or piecewise continuous function, actually, but we'll talk about continuity later. So it is just x if x is greater than or equal to 0, and it is negative x if x is less than 0. So if x is already positive, don't do anything. If x is negative, then you want to multiply by negative. It's like, how do you make everything positive? Okay, but then we're going to divide by x. So let's look at this algebraically a little bit, and then we'll do its graph. So, so first, number one, let's suppose or let x be greater than or equal to 0. Oh, and all this stuff down here, I actually don't want you to see it yet. We're going to, this will bring up later. Let's just move that down. That didn't work. Okay, so we'll be doing these problems. I just don't want you to get distracted yet by all those. Okay. And I don't do a lot of editing. It's so time consuming. We'll just roll with it as we would in class. All right. So let x be greater than 0. Then what do we know? So then you'd write f of x equal to absolute value of x over, oops, let's fix that. So it's absolute value of x over x. But then if it's already positive, then you would say it's just x over x, which is equal to 1. Now, 2, let's suppose or let x be strictly less than 0. Do you already see right here we can't have x be 0, or you divide by 0? So that's already, right, we're actually approaching 0, so we want to see what happens. So then you'd have f of x equal to absolute value of x over x. But by the definition, if you are less than 0, then you're negative x. So this is negative x over x, which is negative 1. So what does that graph look like? So we graph it, and it looked like this. So you can do a lot of these functions, x and y. So if x is greater than 0, so we're talking about these values, but not equal to 0, not here, then you get 1. So we'll be up at 1. Let's just zoom in, not including that, and it's just this line. So that is just y equals 1. At less than 0 to the left, you get just negative 1. So it would be here and to the left. So let's ask the question. As you approach or get close to 0, does the function value approach a specific number? And the answer is no, because if you're approaching like this on the right, okay, so approaching like this on the right, you get 1. If you're approaching like this on the left, you get negative 1. So it does not approach a specific number. Okay, so this is 1 and this is negative 1. Now some of you may know, and we'll get to this later, a few sections ahead, there is such a thing as a right and left limit, and we'll define that later. But just as we are talking about this original concept, if you approach a number on either side, it has to approach the same thing. So can we make the function value of f as close to L as desired by choosing x sufficiently close to A? And it must work on both sides for this definition here to exist. Okay, so that's how you'd show it does not exist. And the write-up would look something like this. So I want to be clear on how you communicate your math, which is what you're trying to get to more and more now. The limit does not exist at 0 since either side of x equals 0 gives a different value for f. Okay, and that's just a way of saying it. So if I want an explanation, that's what I mean. Let's look at another one before we go on to some examples that we'll do in the problem sessions. So let's look at this one. What about limit? This one might say something like investigate the limit. 1 over x squared as x approaches 0. So we need a function. So let's let f of x be 1 over x squared. And then in this case, we're just going to graph that thing. So there's multiple ways of graphing it. You want to review all your functions and special functions to graph. There's a lot, and we can talk about that later, I suppose. But you want to know 1 over x, and if you square it, it's just going to make values do it quicker. So everything's positive, so it basically looks like this and like this. Okay, so you can graph that on really anything. Many of these you just need to know them to do it quickly, not have to graph everything in the sun. So it looks like that. And so what's happening as we approach on either side? What's happening to the function? So if you substitute in values like 0.0001 over here, the function, you flip that, right? So you get 1, 0, 0, 0, 0, 0. So it's getting very large. So this is approaching infinity is what it's doing, right? So that's another type of limit we'll talk about. So this limit actually will say equals infinity, therefore, oops, if I tell you what that means. That means therefore does not exist. I should put that in my my little note thing. Okay, so remember that too. So this is what we call unbounded behavior. Okay, moving along. Next thing I want to look at is oscillating behavior. And we'll do this just graphically. So let's move this one up to here. And then we'll show it algebraically if you want to see all that stuff. These are the problems I'm going to want you to do. Well, we will be doing in problem sessions, and then I'll also show you how you show something like this algebraically, what's going on. So we'll cover all of this in problem sessions. Okay, but one last thing in this this part before we go on to the next one, which I still got to cover. Still need to cover properties of limits. I'll probably do one more for that. Okay, so let's look at sine of 1 over x. Okay, so hold on a second here. Let's see. All right, we're going to go ahead and stop and start again.